In the infinite darkness of space, where human eyes have struggled for millennia to pierce the veil of cosmic mystery, something impossible has emerged from the data streams of our most sophisticated telescope. The James Webb Space Telescope, humanity's golden eye peering into the deepest recesses of time itself, has transmitted images that should not exist. Cannot exist. Yet there they are, glowing on our screens like ancient ghosts refusing to fade into the background radiation of accepted theory. Galaxies. Fully formed, massive, impossibly organized galaxies. But here is where reality fractures, where our comfortable understanding of the universe splinters like ice under pressure. These galaxies are old. Not just old in the way we casually speak of ancient things, but old in a way that makes physicists wake up at night, staring at their ceilings, questioning everything they thought they knew. These structures appear to exist at a time when, according to our most fundamental theories, they simply could not have formed yet. The contradiction burns through the scientific community like wildfire through dry timber. How can something exist before it had time to be created? It's as if we discovered a photograph of your grandmother taken before her parents were born, as if we found a tree whose rings count back further than the age of the forest itself. The Big Bang, that primordial explosion that we have taught in every classroom, written in every textbook, described as the absolute beginning of everything, suddenly seems less like an unshakable foundation and more like a chapter in a much longer story. A story we never knew we were missing. Imagine, if you will, standing at the edge of an ocean. For your entire life, you've been told that beyond the visible horizon lies nothing but more water, eventually reaching distant shores we can map and predict. The ocean, in this metaphor, is time itself. The Big Bang is supposed to be the shore behind you, the solid ground from which everything originated, approximately 13.8 billion years ago. Every wave, every ripple, every movement in that cosmic ocean originated from that singular shore. Or so we thought. Now picture turning around and discovering footprints in that sand leading backward, disappearing into cliffs that shouldn't exist, suggesting something walked there before the shore was formed. This is the magnitude of what Webb has shown us. The old theory was so elegant, so mathematically beautiful, that it seduced generations of scientists into comfortable certainty. The universe began in a point of infinite density and temperature. Time itself had no meaning before this moment. Everything that exists, every atom in your body, every photon from distant stars, every force and field and fundamental particle, emerged from this singular event. The universe expanded, cooling as it grew, and in that cooling, the first particles formed. Protons found electrons. Hydrogen condensed from the cosmic fog. Then, slowly, painstakingly slowly, gravity began its patient work of pulling matter together. The first stars would have been massive, primitive things, fusing hydrogen in their cores, creating heavier elements, living fast and dying young in spectacular supernovae that seeded the cosmos with the building blocks of complexity. Then, from this enriched material, the first galaxies would have assembled themselves, drawn together by dark matter's invisible scaffolding, over hundreds of millions of years. This timeline was not guesswork. It was built on decades of observation, on mathematical models tested and retested, on the cosmic microwave background radiation, that faint afterglow of creation itself, which we can still detect today. We could see the baby universe, just 380,000 years old, in that ancient light. We could measure its temperature fluctuations, its density variations, and from these measurements, we could predict how long it would take for galaxies to form. The calculations were clear. The math was rigorous. Galaxies, especially large, mature galaxies with complex structures, should not appear until at least several 100 million years after the Big Bang. It takes time for gravity to pull gas clouds together. It takes time for stars to form and die and form again. It takes time for galactic disks to organize themselves, for spiral arms to sweep through stellar neighborhoods, for supermassive black holes to grow at galactic centers. But Webb's images tell a different story. A troubling, exhilarating, fundamentally disturbing story. The telescope's infrared eyes, sensitive to wavelengths of light that have been stretched by the universe's expansion over billions of years, can see further back in time than any instrument humans have ever constructed. When we look at distant galaxies, we are not seeing them as they are now. We are seeing them as they were when their light first began its journey toward us. Look at a galaxy 13 billion light-years away, and you are looking 13 billion years into the past. Webb was designed specifically to look at this ancient era, to witness the formation of the first stars and galaxies, to see cosmic dawn breaking across the infant universe. Scientists expected to find small, irregular proto-galaxies, the primitive ancestors of the grand structures we see in the nearby universe today. They expected to see the universe in its awkward adolescence, all ungainly proportions and incomplete development. What they found instead defies these expectations so dramatically that some researchers initially thought there must be errors in the data. The galaxies Webb observed from the universe's first few 100 million years are not small. They are not primitive. They are massive, some containing billions of stars, exhibiting the kind of structural sophistication that should have required billions of years to develop. Spiral arms. Central bulges. Regular, organized distributions of stellar populations. These are not the characteristics of newborn galaxies still figuring out how to exist. These are mature systems, galaxies that look like they've lived long, complex lives. But they exist at a time labeled 600 million years after the Big Bang on our cosmic calendar. That might sound like a long time, but in the context of galaxy formation as we understood it, 600 million years is barely enough time for the first generation of stars to complete their life cycles. It's certainly not enough time for billions of stars to organize themselves into the majestic structures we're seeing. Think of it this way: imagine telling a biologist that you found a fully developed oak tree, complete with thick trunk, spreading branches, and deep root system, growing in soil that formed only 5 years ago. The biologist would tell you that's impossible. Oak trees take decades to develop that kind of structure. The soil itself needs time to develop the nutrient profile that can support such growth. Finding your oak tree would require rewriting fundamental assumptions about botanical development, about soil formation, about the very process of growth itself. This is the situation astronomers find themselves in today. The galaxies are the oak trees. The early universe is the 5-year-old soil. And the theories we've built our entire understanding upon are suddenly inadequate to explain what we're observing. So what could this mean? What are the possibilities that emerge from this impossible observation? The mind reels at the implications, each one more profound than the last. Perhaps the Big Bang was not the beginning we thought it was. Perhaps it was a transition, a phase change in a universe that already existed in some form we cannot yet comprehend. Imagine a cosmic reset button, where matter and energy were reorganized but not created from nothing. Some theories in physics have long suggested this possibility, proposing cyclical universes that expand and contract in eternal rhythms, each Big Bang the echo of a previous universe's death. In such a scenario, structures from a previous cosmic cycle might have persisted somehow, serving as seeds for the rapid galaxy formation we're now observing. The galaxies we see might not be 600 million years old at all. They might be artifacts carrying imprints of something far more ancient, ghosts from a universe before our universe. Or consider another possibility, equally unsettling: what if time itself behaved differently in the early universe? Our theories assume that the laws of physics, including the passage of time, have remained constant since the Big Bang. But what if that assumption is wrong? What if time ran faster in the universe's youth, allowing processes that should take billions of years to unfold in mere hundreds of millions? It sounds like science fiction, but some theories in physics, particularly those dealing with quantum gravity and the early universe's extreme conditions, suggest that time might not be the universal constant we experience in our everyday lives. If time was somehow compressed or accelerated in the early universe, then perhaps these mature galaxies did have the billions of years they needed to form, packed into a much shorter period by our current reckoning. Then there's the dark matter question, that persistent enigma that has haunted cosmology for decades. We know dark matter exists. We can measure its gravitational effects. Galaxies spin too fast to be held together by the gravity of their visible matter alone. Galaxy clusters bend light in ways that require far more mass than we can see. Something invisible, something that doesn't interact with light, makes up approximately 85% of the universe's matter. But we don't know what it is. We've never detected a dark matter particle directly. What if dark matter behaved very differently in the early universe? What if it clumped together faster than our models predict, creating dense gravitational wells that could have pulled normal matter together at accelerated rates? If dark matter could form structures more quickly than we thought possible, it might have provided the scaffolding for rapid galaxy formation, allowing these massive galaxies to appear far earlier than conventional theories allow. Some scientists are proposing even more radical revisions to our understanding. What if the constants of nature themselves, those fundamental numbers that govern everything from the strength of gravity to the mass of electrons, were different in the early universe? We assume these constants have always had the same values they have today. But assumption is not proof. If gravity was stronger in the early universe, even slightly stronger, it would have pulled matter together more quickly. If the physics governing star formation were subtly different, stars might have formed more efficiently, populating galaxies faster than our current models predict. Changing these fundamental parameters even a little bit could have enormous effects on how quickly complex structures emerge from the primordial chaos. But here's where the story becomes even stranger, even more layered with mystery. The galaxies Webb is seeing are not just unexpectedly large and mature. They're also unexpectedly numerous. Computer simulations of the early universe, based on our best understanding of cosmology, predict a certain number of galaxies should exist at various times in cosmic history. These simulations have been refined over decades, incorporating the latest observations and the most sophisticated physics. They've been remarkably successful at matching what we observe in the nearby, more recent universe. But when we look at Webb's data from the early universe, we see far more galaxies than these simulations predict. It's not a small discrepancy. Some estimates suggest there might be 10 times more galaxies in the early universe than our theories can account for. 10 times more. Let that sink in for a moment. This isn't a minor calibration issue, a small error in our calculations that can be fixed with some adjustments. This suggests that our fundamental understanding of how galaxies form and evolve might be profoundly incomplete. It's as if census takers went to count the population of a city and found 10 times more people than all their demographic models predicted possible. At that point, you're not just tweaking your model. You're questioning whether you understand population growth at all. The challenge for scientists now is profound. How do you revise a theory that has been so successful in explaining so many observations? The Big Bang model, with all its refinements and additions over the decades, has passed countless tests. It explains the cosmic microwave background radiation. It explains the abundance of light elements like hydrogen and helium. It explains the large-scale structure of the universe, the way galaxies are distributed throughout space in a vast cosmic web. It explains the expansion of the universe, the observation that more distant galaxies are moving away from us faster, their light stretched toward redder wavelengths by the Doppler effect. All of this fits together in a coherent framework that has guided astronomical research for generations. Yet Webb's observations suggest that something fundamental is missing from this framework. It's not that the entire Big Bang theory is wrong, necessarily. The evidence supporting the universe's expansion and its hot, dense beginning remains strong. But clearly, our understanding of what happened in the first billion years after that beginning is incomplete. We're missing something crucial, some piece of physics or some cosmic process that allowed galaxies to form and grow much faster than our current theories permit. Consider the problem from another angle: the impossible stars that some researchers claim to have found in Webb's data. Not just galaxies, but individual stars that appear to be extraordinarily massive, perhaps hundreds of times the mass of our Sun, existing in the very early universe. These would be what astronomers call population 3 stars, the hypothetical first generation of stars that formed from the pristine hydrogen and helium created in the Big Bang, before any heavier elements existed. We've never directly observed a population 3 star. All the stars we can see in our own galaxy are enriched with heavier elements, the products of earlier stellar generations. But theory predicts that population 3 stars should have been massive, short-lived, and very different from stars that formed later in cosmic history. What's shocking about some of Webb's observations is that if these really are population 3 stars, they appear to be even more massive than theory predicted, and they seem to have formed in greater numbers. Massive stars are cosmically important because they live fast and die young, exploding as supernovae and enriching the interstellar medium with heavy elements. The more massive stars you have in the early universe, the faster you can produce the chemical diversity needed for planet formation, for complex chemistry, ultimately for life. If the early universe was churning out massive stars at rates higher than we expected, it could help explain how galaxies grew so large so quickly. But it also raises new questions: how do you form such massive stars? Current star formation theory suggests there should be limits on how large a star can grow. If the early universe was routinely violating these limits, what does that tell us about conditions in that distant era? The emotional weight of these discoveries cannot be understated. For scientists who have spent their entire careers building and refining the standard cosmological model, Webb's observations represent both a crisis and an opportunity. A crisis because cherished theories are being challenged, because the universe is refusing to behave according to the rules we thought we understood. But also an opportunity, because moments like these, when observations clash with theory, are when science makes its greatest leaps forward. History is full of examples. The orbit of Mercury didn't quite match Newtonian predictions, and that discrepancy ultimately led Einstein to develop general relativity, revolutionizing our understanding of gravity, space, and time. The spectrum of blackbody radiation couldn't be explained by classical physics, and that puzzle gave birth to quantum mechanics, revealing the bizarre rules that govern the atomic realm. Now, the early galaxies that shouldn't exist are forcing us towards some new understanding, some deeper truth about the universe that we haven't grasped yet. What might that new understanding look like? Some possibilities are conservative, requiring only modest modifications to existing theories. Perhaps our models of star formation need adjustment. Perhaps gas clouds in the early universe could collapse into stars more efficiently than we thought, thanks to physics we haven't fully accounted for. Perhaps supermassive black holes, those enigmatic monsters that lurk at the centers of galaxies, formed earlier and grew faster than our theories predict, and their powerful influence helped organize galaxies more quickly. Black holes, despite their reputation for destroying everything that falls into them, can also play constructive roles in galaxy formation. The jets of matter and energy they spew out can trigger star formation in surrounding gas clouds. If supermassive black holes appeared very early in the universe and grew rapidly, they might have served as engines driving accelerated galaxy development. Other possibilities are far more radical, requiring us to reconsider fundamental aspects of cosmology. Some researchers are revisiting old ideas that fell out of favor, wondering if they deserve another look in light of Webb's observations. There's the concept of primordial black holes, for instance, the idea that black holes formed not from stellar collapse but directly from extreme density fluctuations in the early universe, perhaps even before the first stars ignited. If such black holes existed in great numbers, they could have served as gravitational seeds around which matter quickly accumulated, jump-starting galaxy formation. There are theories involving modifications to gravity itself at cosmic scales, alternatives to general relativity that might predict faster structure formation. There are even more exotic ideas involving extra dimensions, quantum effects on cosmological scales, or entirely new fields and forces that only manifest at the extreme energies present in the very early universe. The truth is, we don't know yet which of these possibilities, if any, will prove correct. We're in a period of profound uncertainty, and that uncertainty is both humbling and exhilarating. For the general public, it might seem disturbing that scientists don't have immediate answers, that the experts are admitting confusion. But this is actually how science works at its best. Real scientific progress doesn't come from having all the answers. It comes from asking better questions, from being willing to say, "We don't know," and then pursuing that ignorance with rigor and creativity. The scientists working on this problem aren't throwing up their hands in despair. They're energized. They're developing new theories, running new simulations, proposing new observations, engaging in heated debates at conferences, staying up late running calculations, trying to find the missing piece of the cosmic puzzle. Let's delve deeper into what these early galaxies actually look like, because the details matter. When Webb captures an image of a distant galaxy, it's not like taking a photograph with your phone. The light has been traveling through expanding space for billions of years, and that expansion has stretched the light waves, shifting them from visible wavelengths toward the infrared. This is redshift, and it's one of the most important concepts in modern cosmology. The more redshift a galaxy shows, the more distant it is, and therefore the further back in time we're seeing. Webb is optimized for infrared observation precisely because this is the wavelength range where we can detect the most distant, earliest structures in the universe. The galaxies Webb is finding have redshifts of 10, 12, even higher in some cases. These numbers correspond to times when the universe was only a few 100 million years old, mere infants by cosmic standards. But when astronomers analyze the light from these galaxies in detail, using spectroscopy to break it down into its component wavelengths, they find chemical signatures that shouldn't be there so early. They find evidence of elements heavier than hydrogen and helium, elements that can only be created in stellar interiors and dispersed through supernova explosions. The presence of these elements indicates that multiple generations of stars must have already lived and died in these galaxies. This is not the pristine, first-generation star formation we expected to see. This is a universe that has already been through some cosmic processing, already been enriched by stellar alchemy. And that processing takes time. More time than these galaxies have supposedly had. Some of these early galaxies also show evidence of dust, those microscopic particles of carbon, silicon, and other elements that form in the atmospheres of dying stars and in supernova ejecta. Dust is important in the universe because it's where much of chemistry happens, where molecules can form in the interstellar medium. But dust, like heavy elements, is a product of stellar evolution. You don't get dust without first having stars that create heavy elements, then die and release those elements into space, where they can condense into tiny grains. Finding significant amounts of dust in galaxies that are supposedly only a few 100 million years old is another piece of evidence that something is off in our timeline. Either these galaxies are older than their measured distances suggest, which would require rethinking how we interpret redshift and cosmic expansion, or they went through stellar evolution much faster than our theories predict, which would require rethinking star formation, stellar life cycles, and chemical enrichment processes. There's also the morphology issue, the shapes and structures of these early galaxies. When you look at images of the very distant universe taken by earlier telescopes like Hubble, you see galaxies that are generally small, irregular, chaotic-looking things. They appear to be in the process of merging and colliding, building themselves up through violent interactions. This fits with our theories of hierarchical structure formation, the idea that small structures form first and then merge to create larger structures over time. The early universe should be dominated by these small, messy proto-galaxies, gradually assembling themselves into the grand spirals and ellipticals we see in the nearby universe. But Webb is showing us galaxies that don't fit this picture. Some of them have clear spiral structures, well-defined disks, central bulges. These are features that take time to develop, that require a galaxy to settle down into a stable configuration after the turbulent violence of its formation. Seeing such mature morphologies so early is like finding ancient ruins built with architectural sophistication when you expected to find only primitive cave dwellings. It suggests that either galaxies can organize themselves much faster than we thought, or that the early universe was less chaotic than our models predicted, or that we're fundamentally misunderstanding something about how galaxies develop their structures. The mass estimates for these early galaxies are equally problematic. When astronomers measure how many stars are in a galaxy, they use several techniques. They can look at the total light output and use models of stellar populations to estimate how many stars of various types would be needed to produce that much light. They can study the kinematics, how fast stars and gas are moving within the galaxy, which tells them about the gravitational mass holding everything together. They can look at the chemical composition and use what we know about stellar evolution to infer the history of star formation. All of these methods require assumptions, and those assumptions are based on our understanding of how stars and galaxies work. But when applied to these early Webb galaxies, they yield masses that seem impossibly high for the age of the universe at that time. Some of these galaxies appear to contain tens of billions of stars, perhaps even hundreds of billions. Our own Milky Way galaxy, a large and mature spiral that has been forming stars for most of cosmic history, contains somewhere between 100 and 400 billion stars. The idea that galaxies of comparable mass could exist when the universe was less than a billion years old is staggering. To form that many stars that quickly would require extremely efficient star formation, converting enormous amounts of gas into stars at rates much higher than what we observe in the nearby universe today. It would also require having that much gas available in the first place, concentrated in a relatively small region of space. Where did all that gas come from? How did it accumulate so quickly? These are questions that current models struggle to answer. Perhaps the answer lies in the invisible realm, in the dark matter that dominates the universe's mass budget but remains frustratingly elusive to direct detection. We know dark matter exists from gravitational evidence, but we don't know what it's made of. The leading candidate is something called cold dark matter, consisting of particles that move slowly relative to the speed of light and clump together through gravity. Cold dark matter forms halos, vast spherical regions where dark matter accumulates, and these halos serve as the gravitational wells into which normal matter falls, eventually forming galaxies. Computer simulations of structure formation, using cold dark matter assumptions, have been remarkably successful at reproducing the large-scale distribution of galaxies in the universe. But maybe cold dark matter doesn't tell the whole story. There are alternative ideas about dark matter's properties that could affect how quickly structures form. What if dark matter particles can interact with each other in ways beyond just gravity? What if there are dark forces, analogous to the electromagnetic force but acting only on dark matter, that could affect how dark matter clumps? Such interactions could potentially speed up or slow down structure formation in ways that our standard cold dark matter models don't account for. Or what if dark matter is not just one type of particle but a whole dark sector, a hidden realm of particles and forces that mirrors the complexity of the visible sector we're familiar with? Some theoretical physicists have proposed that dark matter might make up entire dark atoms, dark molecules, even dark planets or dark stars. If the dark sector is that rich, it might have its own complicated dynamics that could influence structure formation in unexpected ways. Another intriguing possibility involves what's called warm dark matter or hot dark matter, consisting of particles that move faster than the cold dark matter particles. The speed at which dark matter particles move affects how they clump. Faster-moving particles smooth out small-scale density fluctuations, making it harder for small structures to form, but they might allow larger structures to form more easily. Most cosmological evidence favors cold dark matter, but if there's even a small component of warm or hot dark matter mixed in, it could alter the timeline of structure formation in ways that might help explain Webb's observations. Then there's the question of dark energy, that mysterious force driving the universe's accelerated expansion. We know even less about dark energy than we do about dark matter. We know it exists because we can measure its effects, the fact that distant supernovae appear dimmer than they should be if the universe's expansion were slowing down under gravity's influence. Instead, the expansion is speeding up, as if something is pushing the universe apart. We call this something dark energy, and it makes up approximately 70% of the universe's total energy budget. The simplest explanation for dark energy is that it's a cosmological constant, a property of space itself that doesn't change over time. But what if dark energy wasn't constant in the early universe? What if it behaved differently when the cosmos was young? If dark energy was weaker in the early universe, or if it operated differently, it could have allowed matter to clump together more easily in that distant era. Less dark energy pushing things apart would mean more efficient structure formation driven by gravity pulling things together. As the universe aged and dark energy grew stronger or changed its properties, structure formation would slow down, eventually reaching the rates we observe in the nearby universe today. This would create a window of opportunity in the early universe, a period when galaxies could form and grow quickly before dark energy's influence became dominant. It's a speculative idea, and it would require modifying our understanding of dark energy in significant ways, but it's the kind of creative thinking that's needed when observations challenge established theories. We should also consider the role of primordial magnetic fields. Magnetic fields permeate the universe. We can detect them in galaxies, in galaxy clusters, even in the intergalactic medium. But where did these magnetic fields come from originally? One possibility is that weak magnetic fields existed even in the very early universe, perhaps generated by quantum fluctuations during cosmic inflation, that brief period of exponential expansion that's thought to have occurred fractions of a second after the Big Bang. If such primordial magnetic fields existed, they could have influenced how matter clumped together in the early universe. Magnetic fields can affect the motion of ionized gas, channeling it along field lines, potentially speeding up the collapse of gas clouds into stars. They can also help remove angular momentum from collapsing systems, which is one of the key challenges in star and galaxy formation. Material tends to conserve its angular momentum as it falls inward, causing it to spin faster and faster, which can prevent further collapse. Magnetic fields provide a way to transport that angular momentum outward, allowing material to continue falling in and forming dense objects. If primordial magnetic fields were stronger than we've assumed, or if they had particular configurations that made them especially effective at facilitating structure formation, they could potentially help explain rapid early galaxy growth. This is another area where Webb's observations might be pointing us toward overlooked physics, subtle effects that become important under the extreme conditions of the early universe but are less significant in the calmer, more evolved cosmos we see around us today. Let's return to the philosophical dimension of what's happening here, because these are not just technical questions for specialists. These discoveries strike at the heart of how we understand our place in the universe. For centuries, humans have grappled with our cosmic significance. We've gone from thinking Earth was the center of everything to realizing we live on an ordinary planet orbiting an ordinary star in an ordinary galaxy in an ordinary part of the universe. This progressive decentering, sometimes called the Copernican principle, has been humbling but also liberating. It's freed us from parochial thinking and opened our eyes to the vast scales and deep history of the cosmos. But the Copernican principle also brings with it certain assumptions. We assume that the laws of physics are the same everywhere and everywhen. We assume that what we see in our cosmic neighborhood is representative of the universe as a whole. We assume that the processes happening now operated in the same way in the distant past. These assumptions have been incredibly productive. They've allowed us to make testable predictions and build coherent models of cosmic evolution. But what if these assumptions need refinement? What if the early universe was genuinely different in ways that our principle of cosmic mediocrity doesn't capture? Webb's observations might be telling us that the universe's first billion years were special, characterized by physics or conditions that don't persist into later cosmic epochs. This wouldn't invalidate the Copernican principle entirely, but it would add nuance to it. It would suggest that while the laws of physics are universal, their consequences can vary dramatically depending on the environment. The early universe, with its higher densities, hotter temperatures, and different mix of matter and radiation, might have been a realm where processes we consider exotic today were commonplace. As the universe expanded and cooled, those special conditions faded, and cosmic evolution entered the slower, steadier phase we observe in more recent epochs. This brings us to the anthropic question, the question of fine-tuning in cosmic habitability. One of the most puzzling aspects of our universe is how precisely calibrated everything seems to be for the emergence of complexity and life. The fundamental constants of nature, the masses of particles, the strengths of forces, all have values that appear to be exquisitely tuned. Change any of these values by even small amounts, and you get a universe that's hostile to structure formation. Make gravity slightly stronger, and stars burn out too quickly for life to evolve. Make it slightly weaker, and stars never form at all. Make the electromagnetic force stronger, and chemical bonding becomes impossible. Make it weaker, and atoms fly apart. The list of such fine-tunings is long and disturbing to some physicists, because it seems to require explanation. One proposed explanation is the multiverse, the idea that our universe is just one of countless universes, each with different values for their fundamental parameters. In this view, we find ourselves in a universe with life-friendly parameters not because those parameters are special in any absolute sense, but because those are the only kinds of universes where observers like us can exist to ask the question. This anthropic reasoning is controversial in physics, with some embracing it as a legitimate explanatory principle and others rejecting it as unscientific since other universes are, by definition, unobservable from our own. But Webb's discoveries add a new wrinkle to these anthropic considerations. If galaxies can form much faster than we thought, if the early universe was more efficient at building complex structures, this potentially expands the range of possible universes that could support life. It suggests that cosmic evolution might be more robust, less sensitive to initial conditions, than we previously believed. Or conversely, it might indicate that our universe is even more special than we realized, with properties in the early universe that allowed rapid structure formation in ways that wouldn't work with slightly different parameters. The implications for the anthropic debate are still unclear, but they're profound. There's also a historical dimension worth exploring. This is not the first time astronomical observations have challenged the Big Bang model, forcing revisions and refinements. In the 1990s, measurements of the Hubble constant, the rate at which the universe is expanding, suggested the universe was younger than some of the stars within it, an obvious impossibility that came to be known as the age problem. The resolution involved both better measurements of cosmic distances and the discovery of dark energy, which accelerated the universe's expansion and effectively made the universe older than earlier estimates suggested. In the 1970s and 80s, the flatness problem and the horizon problem threatened to undermine the Big Bang theory, leading to the development of cosmic inflation as a solution. Inflation, that brief period of exponential expansion in the universe's first moments, solved multiple theoretical problems and made predictions that were later confirmed by observations of the cosmic microwave background. The point is that the Big Bang model has been challenged before and has emerged stronger, incorporating new physics and new insights. The current challenge from Webb might be the most serious yet, but history suggests that it will lead to a deeper, richer understanding rather than a complete abandonment of the framework. Science progresses not by clinging to theories despite contradictory evidence but by being willing to revise and refine those theories when observations demand it. The scientists working on this problem are not defending the Big Bang model out of blind loyalty. They're defending it because it explains so much else so well, and they're actively working to understand how it needs to be modified to accommodate these new observations. Consider the actual process of science happening right now in response to Webb's data. Thousands of researchers around the world are examining these images and spectra, checking the data reduction procedures, verifying the distance estimates, exploring alternative interpretations. Some are developing new theoretical models, writing equations that might explain rapid early structure formation. Others are running massive computer simulations, using supercomputers to model billions of years of cosmic evolution under different assumptions, seeing which assumptions produce results matching Webb's observations. Still others are proposing follow-up observations, identifying specific galaxies or regions of the sky that Webb should examine more closely to test competing hypotheses. This collaborative, sometimes contentious process is science at its finest. There are passionate disagreements about interpretation, about what the data really show, about which theories are most promising. Preprint servers are flooded with new papers proposing different explanations. Conference presentations spark heated debates. Social media sees astronomers arguing about photometric versus spectroscopic redshifts, about stellar population models, about systematic uncertainties in mass estimates. To an outsider, this might look like chaos, like the field is in disarray. But this is actually healthy. This is how science confronts profound challenges, how it works through uncertainty toward better understanding. And let's not forget the engineering triumph that makes all of this possible. The James Webb Space Telescope itself is a monument to human ingenuity and persistence. Decades in development, billions of dollars in cost, countless technical challenges overcome, Webb represents the culmination of efforts by thousands of engineers, scientists, and technicians. The telescope's 18 hexagonal mirror segments, made of beryllium and coated with gold, work together as a single mirror 6.5 meters in diameter, larger than any mirror previously sent into space. The sun shield, as large as a tennis court, keeps the telescope cold enough to detect faint infrared signals from the distant universe. The entire observatory sits at the second Lagrange point, a stable location about 1,000,000 miles from Earth where the gravitational pulls of Earth and Sun balance out. Every component of Webb was pushed to the limits of what's possible. The deployment sequence, where the telescope unfolded itself in space like an intricate piece of origami, involved hundreds of steps, each of which had to work perfectly. There were no second chances, no repair missions possible at this distance. When Webb launched in December 2021, the entire astronomical community held its breath. When the deployment succeeded and the first images were released in July 2022, there was collective celebration. And now, those images are forcing us to reconsider fundamental aspects of cosmology. The telescope is doing exactly what it was designed to do, revolutionizing our view of the universe. But we should be careful about overclaiming. Science journalism, in its eagerness to attract attention, sometimes sensationalizes results, presenting preliminary findings as definitive conclusions. The truth is always more nuanced. Not all astronomers agree that Webb's observations overturn the Big Bang model. Many argue that the observations, while surprising, can be accommodated within the existing framework with some modifications. The galaxies might not be quite as massive as initial estimates suggest. Better modeling of stellar populations and dust effects might reduce the tension with theory. The redshift estimates might have systematic uncertainties that aren't fully accounted for. It's possible that some of what appear to be single massive galaxies are actually multiple smaller galaxies that happen to lie along the same line of sight, visually merged in Webb's images but actually separate objects at different distances. These alternative interpretations need to be explored rigorously. Science demands skepticism, demands that we consider all possible explanations before accepting the most dramatic one. The claim that Webb has found something older than the Big Bang is, at present, more of a provocative headline than a settled conclusion. What's certain is that Webb has found galaxies that are unexpectedly large and mature for their age, according to our current models. Whether this represents a crisis for the Big Bang theory or merely a need for adjustments is still being debated. Yet even if the most conservative interpretations turn out to be correct, even if the tension with theory is resolved with relatively minor modifications, Webb's observations are still profoundly important. They're pushing our models to their limits, testing assumptions, revealing where our understanding is robust and where it needs work. This is invaluable. A theory that's never tested is just speculation. A theory that's tested and passes is strengthened. A theory that's tested and fails is replaced with something better. Webb is providing tests of cosmology more rigorous than anything we've had before, and regardless of the ultimate outcome, our understanding will be deeper for it. Let's explore some of the specific galaxies that have caught researchers' attention. There's one system, given the unwieldy designation Glass Z13, that was among the first candidates for being one of the most distant galaxies ever seen. Follow-up spectroscopy confirmed it exists at a time just 300 million years after the Big Bang. It's a small, compact blob of light in Webb's images, but analysis suggests it contains perhaps 1 billion stars and is forming new stars at a rate hundreds of times higher than our Milky Way does today. How can a galaxy be so active so early? What triggered such intense star formation? Another system, called Source 93316, initially appeared to be even more distant, potentially the most remote galaxy ever detected. Later analysis suggested it might not be quite as far as first thought, but it remains an extremely early galaxy with surprising properties. Its spectrum shows evidence of oxygen, indicating that stars had already lived and died and enriched the interstellar medium with heavy elements. Oxygen is created primarily in massive stars and dispersed when those stars explode as supernovae. Seeing oxygen this early means stellar evolution had already progressed through at least one generation, possibly more. Then there are the galaxy candidates with redshifts of 15 or higher, pushing toward what some call the cosmic dark ages, the period before the first stars formed when the universe was filled with neutral hydrogen gas, opaque to ultraviolet light. If galaxies really exist at such high redshifts, they must have formed incredibly early, perhaps within the first 100 million years of the Big Bang. At these epochs, the cosmic microwave background radiation would have been much hotter than it is today, and this might have affected how gas could cool and collapse to form stars. Current models suggest that in this hot environment, forming stars should have been difficult, requiring especially massive gas clouds to overcome the radiation pressure. Yet if these galaxy candidates are confirmed, they'd indicate that star formation was somehow proceeding efficiently despite these challenges. Some researchers are focusing on the colors of these early galaxies, the way their light is distributed across different wavelengths. Colors tell us about stellar populations, about the ages and types of stars that make up the galaxy. Red colors generally indicate older stars, while blue colors indicate young, hot stars. What's intriguing is that some of Webb's early galaxies show colors that suggest mixed stellar populations, both old and young stars coexisting. This implies that these galaxies have already had complex star formation histories, with multiple bursts of star formation separated by quieter periods. Such complexity is expected in mature galaxies like the Milky Way, which has been forming stars for over 12 billion years. Seeing it in galaxies less than 1 billion years old is another sign that things happen faster in the early universe than our models predict. The role of supermassive black holes in early galaxy formation deserves more attention. We know that most, if not all, large galaxies harbor supermassive black holes at their centers. Our own Milky Way has one, called Sagittarius A-, with a mass about 4 million times that of our Sun. Some galaxies have black holes billions of times the Sun's mass. These black holes are not directly visible, but we can detect them through their gravitational effects on nearby stars and through the radiation emitted by hot gas falling into them. When a supermassive black hole is actively feeding, it creates what we call an active galactic nucleus, or AGN, one of the most luminous phenomena in the universe. The energy output can outshine the entire galaxy's worth of stars. How do supermassive black holes form? This is one of the great unsolved problems in astrophysics. They're too massive to have formed from individual stellar mass black holes through simple growth by accretion. There hasn't been enough time in the universe's history for a black hole that started at a few times the Sun's mass to grow to billions of solar masses, even if it was feeding continuously at the maximum possible rate. This suggests that supermassive black holes must have had more massive beginnings, perhaps forming from the direct collapse of massive gas clouds in the early universe, or from the merger of many stellar mass black holes in dense star clusters, or through some exotic process we haven't thought of yet. Webb is now finding what appear to be active supermassive black holes in extremely early galaxies, black holes that are already millions or tens of millions of times the mass of the Sun when the universe is less than 1 billion years old. This compounds the formation problem. Not only do galaxies appear more mature than expected, but their central black holes do too. Some theories propose that these early black holes grew from seeds that formed directly in the Big Bang's aftermath, primordial black holes that predated stars and galaxies. If such seeds existed and were scattered throughout the early universe, they could have served as the starting points for rapid black hole and galaxy growth. But primordial black holes are hypothetical. We have no direct evidence they exist, and there are observational constraints limiting how common they could be. The connection between black holes and galaxies is intimate and complex. Observations of nearby galaxies show a tight correlation between the mass of a galaxy's central black hole and the mass of its bulge, the central spherical component of stars. This correlation suggests that black holes and galaxies grow together, their evolution intertwined through feedback processes. When a black hole feeds, it releases enormous energy that heats gas in the galaxy, potentially blowing it out and shutting down star formation. This negative feedback prevents galaxies from growing too large and regulates the black hole's own growth by limiting its food supply. But there's also positive feedback. The outflows and jets from active black holes can compress gas clouds, triggering star formation. The interplay of these effects shapes galaxy evolution in fundamental ways. If supermassive black holes were present very early, they could have played crucial roles in rapid galaxy assembly. Their gravity would help concentrate gas. Their energy output would affect star formation rates and patterns. Their growth would be tied to the growth of their host galaxies. Some models now propose that in the early universe, before feedback effects became well established, there might have been a golden age where black holes and galaxies could grow together quickly, reaching large masses before self-regulation kicked in. This could explain both the massive early galaxies and their massive black holes. But it requires that black hole seeds existed very early and grew very efficiently, which brings us back to the seed formation problem. There's a fascinating interplay between observation and theory happening here. Theorists propose mechanisms for rapid early galaxy formation. Observers use Webb to look for evidence of those mechanisms. If the evidence doesn't match, theorists revise their models and make new predictions, which observers test with further observations. It's an iterative process, a dance between data and ideas, each informing the other, gradually converging on truth. We're in the early stages of this dance with Webb. The first observations surprised us. Now we're scrambling to understand them, proposing explanations, testing those explanations, refining them. It will take years, perhaps decades, before the dust settles and we have a new consensus model that explains everything we're seeing. Meanwhile, Webb continues to observe, accumulating more data, finding more distant galaxies, revealing more details about the early universe. Every observing program adds to our knowledge. Some programs target specific distant galaxies for detailed spectroscopic study, breaking their light into component wavelengths to measure precise distances and chemical compositions. Other programs survey large areas of sky, looking for rare objects, compiling statistical samples that can test theoretical predictions. Still others focus on nearby galaxies, studying them in unprecedented detail to understand processes that might also be happening in those distant systems we can barely resolve. The beauty of Webb is its versatility. It can do both deep, narrow studies of individual objects and wide, shallow surveys of many objects. It can observe in multiple infrared wavelengths simultaneously, building up rich datasets that reveal different aspects of what it's looking at. Its spectroscopic capabilities allow it to dissect light with precision, identifying specific atoms and molecules, measuring velocities, temperatures, densities. Every observation is carefully planned, maximizing scientific return, because time on Webb is precious. Thousands of astronomers around the world compete for observing time, proposing programs, arguing their scientific merits. Only the best proposals are selected, ensuring that the telescope is used efficiently to address the most pressing questions. And yet, for all its capabilities, Webb has limitations. It cannot observe visible light or ultraviolet light, only infrared. This means it cannot see the hottest, youngest, most massive stars directly, because those stars emit most of their light at shorter wavelengths. It has to infer their presence indirectly. Webb also has a finite resolution, a limit to how much detail it can see. Very distant galaxies appear as small, fuzzy blobs, and teasing out their internal structure requires sophisticated analysis and modeling. And there are simply limits to how faint an object Webb can detect, limits set by the photons trickling in from across billions of light-years and the unavoidable noise in the detectors. Future observatories will push these limits further. Plans are already being discussed for next-generation space telescopes with even larger mirrors, more sensitive detectors, capabilities complementary to Webb. Ground-based observatories are being built with 30-meter-class mirrors and adaptive optics systems that correct for atmospheric distortion, achieving resolutions rivaling space telescopes in some wavelengths. Radio telescope arrays are mapping the distribution of neutral hydrogen in the early universe, tracing where gas was concentrated before stars formed. Gravitational wave detectors are opening entirely new windows on the universe, detecting ripples in spacetime from colliding black holes and neutron stars, potentially even from the Big Bang itself. All of these tools together will give us an increasingly complete picture of cosmic history. Webb's discoveries are just one piece of a larger puzzle. They're an important piece, a dramatic piece, a piece that's forcing us to reconsider our assumptions. But the full picture will emerge only when we integrate Webb's data with observations from other telescopes, with theoretical modeling, with computer simulations, with laboratory experiments testing fundamental physics. Science is collaborative and cumulative, building knowledge brick by brick, sometimes having to tear down sections when we realize the foundation isn't solid, then rebuilding with better materials and deeper understanding. What about the cosmic microwave background, that faint glow of radiation left over from the early universe? How does it fit into this puzzle? The CMB is one of the strongest pieces of evidence for the Big Bang model. It was predicted theoretically decades before it was observed, a prediction that came true when Penzias and Wilson accidentally discovered it in 1964 while trying to eliminate noise from their radio antenna. The CMB shows us the universe as it was just 380,000 years after the Big Bang, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination, the universe was a hot plasma, opaque to light because photons kept scattering off free electrons. After recombination, the photons could travel freely, and those photons are what we detect today as the CMB, cooled by expansion to a temperature of just 2.7 degrees above absolute zero. The CMB is remarkably uniform, the same temperature in every direction to within 1 part in 100,000. But there are tiny fluctuations, slightly hotter and cooler spots, and these fluctuations are incredibly informative. They represent density variations in the early universe, regions that were slightly more or less dense than average. These density variations are the seeds of all structure in the universe. Slightly overdense regions had a bit more gravity, attracting more matter, growing denser over time, eventually collapsing into the first stars, galaxies, and galaxy clusters. Slightly underdense regions became the cosmic voids, the empty spaces between galaxy clusters. By analyzing the pattern of CMB fluctuations in exquisite detail, cosmologists can determine all sorts of parameters about the universe: its age, its composition, how fast it's expanding, the ratio of matter to dark energy, the density of dark matter, and more. These measurements have been refined over decades by satellites like COBE, WMAP, and Planck. The results are remarkably consistent with the standard Big Bang cosmology, and they're incredibly precise. We know the universe's age to within about 1%. We know how much dark matter and dark energy it contains to similar precision. These are not vague guesses but rigorously determined values that fit together in a coherent framework. But here's the tension: the same cosmological parameters that fit the CMB data so well are the parameters that go into computer simulations of structure formation. And those simulations predict that galaxies should not be as large and numerous in the early universe as Webb is finding. So we have a conflict. The CMB is telling us one thing about the universe's parameters and evolution. Webb is telling us something apparently contradictory. Both can't be fully right as currently interpreted. One resolution is that the CMB measurements are correct, but our models of how structure forms from those initial conditions are incomplete. Maybe there's some physics in structure formation that we're not accounting for, some process that allows galaxies to form faster without changing the fundamental cosmological parameters. This is the conservative view, the one that tries to preserve as much of the existing framework as possible while making targeted modifications. Another resolution is that there's something wrong with how we interpret either the CMB or Webb's data or both. Maybe there are systematic errors in our distance measurements for these early galaxies, making them appear more distant and therefore younger than they really are. Maybe there are selection effects, where we're preferentially finding the most extreme, atypical galaxies in the early universe, giving us a biased view of what early galaxy populations looked like on average. Maybe the models we use to estimate galaxy masses from their light are systematically overestimating those masses in the early universe environment. Or maybe, And this is the most radical possibility: there's something fundamentally wrong with our cosmological model. Maybe the universe's expansion history is not what we think it is. Maybe dark energy or dark matter behave differently than we assume. Maybe there was some early phase of cosmic evolution that's not accounted for in our models, something that happened between the CMB era and the first stars, some process that prepared the universe for rapid structure formation. Distinguishing between these possibilities requires more data. It requires better observations, more distant galaxies studied in more detail, tighter constraints on their properties and ages. It requires better theoretical modeling, exploring a wider range of possible structure formation scenarios. It requires checking and rechecking the measurements, looking for systematic errors, quantifying uncertainties. This work is ongoing. Papers are being published weekly, exploring different aspects of the problem, proposing different solutions, critiquing each other's methods and conclusions. It's messy, but it's progress. Let's think about the human side of this story. There are graduate students who have spent years working on models of early galaxy formation, models that suddenly seem inadequate in light of Webb's observations. Their dissertations may need to be revised or reconceived entirely. That's frustrating, but it's also exciting, because they're living through a period of revolutionary discovery, a time when textbooks are being rewritten. There are senior scientists who built their careers on the standard model of cosmology, who are now grappling with data that challenges core assumptions. Some embrace the challenge, energized by the prospect of new physics. Others are more cautious, reluctant to abandon theories that have served so well. Both reactions are human and understandable. There are instrument scientists who designed and built Webb, who are now seeing their creation exceed expectations, finding things they never anticipated. There's pride there, but also a sense of responsibility to ensure the data is properly calibrated, that artifacts and instrumental effects aren't being mistaken for real cosmic signals. There are theorists who feel vindicated because they proposed alternatives to standard models years ago, ideas that were dismissed as unnecessary complications but now seem newly relevant. And there are observers who spent decades waiting for a telescope like Webb to become reality, who are now seeing the universe with fresh eyes, discovering phenomena they can only begin to interpret. All of these people, with their different perspectives and stakes in the outcome, are contributing to our collective understanding. Science is not a solitary pursuit. It's a community endeavor, requiring cooperation, competition, dialogue, debate. The best ideas survive scrutiny. The weak ideas are discarded or refined. Gradually, consensus emerges, not because everyone agrees from the start, but because evidence accumulates, because arguments are tested, because reality has a way of asserting itself despite our preconceptions. And we should remember that this process has played out before in astronomy's history. When Edwin Hubble first measured the distances to galaxies and discovered the universe is expanding, it revolutionized cosmology. Before Hubble, many scientists believed the universe was static and eternal. Einstein himself found the idea of a changing universe so unsettling that he introduced the cosmological constant into his equations, an ad hoc term to make the universe static. When Hubble's observations proved the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder. Ironically, the cosmological constant was later revived as the simplest explanation for dark energy, so maybe it wasn't such a blunder after all. When Vera Rubin measured rotation curves of galaxies and found they were spinning too fast to be held together by the gravity of visible matter alone, she provided some of the strongest evidence for dark matter. Many astronomers were skeptical at first. Dark matter sounded like a desperate hypothesis, an invisible something invoked to save the theory. But as more evidence accumulated, as alternative explanations failed, the reality of dark matter became accepted. Now it's a cornerstone of cosmology, even though we still don't know what it is. When Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that the universe's expansion is accelerating, it shocked the physics community. Everyone expected gravity to be slowing the expansion down. An accelerating expansion required some form of energy with repulsive gravitational effects, something that pushed rather than pulled. Dark energy was born as a concept, and it remains one of the deepest mysteries in physics. But the observational evidence is solid. The acceleration is real. Each of these discoveries forced revisions to established theories. Each met resistance initially. Each ultimately prevailed because the evidence was compelling. Webb's observations of early galaxies may be following this pattern. They're challenging us, provoking skepticism, demanding explanation. Eventually, through the process of observation, analysis, debate, and synthesis, we'll arrive at a new understanding, one that incorporates these surprising galaxies into a broader framework. It's worth considering what it means to know something in science. Scientific knowledge is not absolute certainty. It's always provisional, always subject to revision in light of new evidence. The best theories are those that make precise, testable predictions, that explain a wide range of phenomena with minimal assumptions, that have survived repeated attempts at falsification. The Big Bang model meets these criteria. It's been tested extensively and has passed most tests. But passing tests doesn't make it unquestionable. When new observations arise that the theory struggles to explain, we don't discard the theory immediately, but we do hold it up to scrutiny, examining its assumptions, looking for places where modifications might be needed. This is very different from how we usually think about knowledge in everyday life. In daily experience, things either are or aren't. The chair you're sitting on is solid. The sun rose this morning. Water is wet. These are facts you don't question. But in science, especially in cosmology where we're dealing with phenomena far removed from everyday experience, our knowledge is always interpreted through models, always mediated by instruments, always dependent on assumptions. The chair is solid because of quantum mechanical principles governing atomic interactions, but at a deeper level, it's mostly empty space. The sun rising is an illusion caused by Earth's rotation, and even Earth's rotation is gradually slowing due to tidal interactions with the moon. Water's wetness is a macroscale property emerging from the particular way water molecules interact with each other and with our skin. Everything has layers, and the deeper you look, the more complex it becomes. In cosmology, we're trying to understand the entire universe, its origin, its evolution, its fate. We're piecing together a story from fragmentary evidence, photons that have traveled billions of years to reach our detectors, mathematical models extrapolated across impossible timescales, experiments on fundamental physics scaled up to cosmic proportions. It's audacious, really, to think we can understand something so vast. Yet we've made remarkable progress. We have a coherent picture of cosmic history, from the Big Bang through the formation of the first atoms, through the Dark Ages and cosmic dawn, through the formation of galaxies and stars, through the emergence of heavy elements and rocky planets, through the origin of life on at least one such planet, through the evolution of intelligence and consciousness and civilization capable of building telescopes and asking these questions. That story, that grand narrative of cosmic evolution, is one of humanity's greatest intellectual achievements. It represents thousands of scientists over generations, building on each other's work, making observations, developing theories, testing predictions, correcting errors, slowly converging on truth. And now that story may need revision in some of its details, maybe even in some of its fundamentals. That's not a failure of the scientific enterprise. That's how the enterprise works. We tell the best story we can with the evidence available. When new evidence arrives, we revise the story. The goal is not to be permanently right but to be progressively less wrong, to get closer and closer to an accurate description of reality. What reality might we be approaching now? What will the new story look like once we've integrated Webb's observations into our cosmological framework? It's too early to say with confidence, but we can sketch some possibilities. Perhaps the story will include a more dynamic early universe, one where structures formed through processes we don't fully understand yet, where feedback effects and nonlinear phenomena played larger roles than we appreciated. Perhaps it will include new physics operating at high energies or early times, exotic particles or fields or interactions that leave their imprint on structure formation. Perhaps it will reveal that the universe's first billion years were genuinely special, a formative period whose conditions and dynamics were qualitatively different from later epochs. Or perhaps the story won't change as dramatically as headlines suggest. Perhaps the solution will be more prosaic, better measurements, refined models, recognition of selection biases or systematic errors, adjustments that bring theory and observation back into alignment without requiring revolutionary new ideas. This would be less exciting in some ways, but it would demonstrate the robustness of the existing framework, its ability to accommodate surprising observations without collapsing. Either way, we learn something valuable. Either we discover new physics and fundamentally deepen our understanding, or we refine our existing understanding and gain confidence in its correctness. Both outcomes advance knowledge. Both are worth the effort. Let's shift perspective and think about what these discoveries mean for the search for life in the universe. If galaxies formed faster than we thought, if heavy elements appeared earlier, if planets could have formed sooner in cosmic history, this potentially extends the window for life to have emerged. Life as we know it requires heavy elements, carbon for complex molecules, oxygen for water and oxidation reactions, nitrogen for nucleic acids and proteins, phosphorus for DNA and ATP, sulfur for amino acids, and so on. All of these elements are created in stars and dispersed through supernovae and stellar winds. If stellar evolution proceeded rapidly in the early universe, if chemical enrichment happened faster, then planets with life-supporting chemistry could have existed earlier than we thought possible. Our Sun and Solar System formed about 4.5 billion years ago, roughly 9 billion years after the Big Bang. Earth is probably not among the universe's first generations of planets. There could be planets billions of years older, orbiting stars in galaxies that formed in the universe's youth. If life emerged on any of those ancient worlds, it would have had billions of extra years to evolve. What might intelligence look like after such vast timescales? What technologies might be developed? What understanding of the universe might be achieved? These questions are speculative, but Webb's observations make them slightly less speculative by suggesting that suitable environments for life might have existed much earlier than previously thought. Of course, this all assumes that life can only emerge in certain kinds of environments, that it requires planets and liquid water and organic chemistry. We have a sample size of 1, Earth, which limits our ability to generalize. Maybe life is far more adaptable than we imagine, able to emerge in exotic environments we haven't considered. Or maybe Earth-specific conditions are so rare that life is extraordinarily uncommon, making our existence a cosmic fluke. We don't know. But we do know that finding habitable planets, planets where conditions might be suitable for life as we understand it, is one of the great quests of contemporary astronomy. Webb is contributing to this quest. It's studying the atmospheres of exoplanets, planets orbiting other stars, looking for chemical signatures that might indicate biological activity. It's not optimized for this task the way future missions will be, but it can still make important contributions, especially for hot, giant planets whose atmospheres are easier to study. Eventually, dedicated missions will search for biosignatures on Earth-like planets in their stars' habitable zones, the regions where temperatures allow liquid water to exist. Finding evidence of life beyond Earth would be one of the most profound discoveries in human history, answering age-old questions about our cosmic solitude. And if intelligent life is common in the universe, where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where are they, given that the universe is so old and so large?" If intelligence commonly arises and develops technology, we might expect to see evidence of it everywhere: massive engineering projects, altered stellar spectra from Dyson spheres capturing stars' energy, radio or optical signals from civilizations trying to communicate, probes or artifacts in our own solar system left by ancient explorers. Yet we see nothing. The skies are silent. This suggests either that intelligent life is very rare, that it typically doesn't last long enough to spread across the galaxy, that it chooses not to reveal itself, or that we're not looking in the right ways or places. Webb's findings don't directly address the Fermi paradox, but they inform it by telling us about the universe's timeline and structure. If galaxies formed early and stars began enriching the cosmos with heavy elements quickly, then habitable planets could have existed for most of cosmic history, giving intelligence many opportunities to arise and spread. The absence of evidence for ancient civilizations despite these opportunities makes the paradox even more puzzling. Maybe intelligence is intrinsically fragile, prone to self-destruction or civilizational collapse before it can become spacefaring. Maybe interstellar travel is far harder than science fiction suggests, making galactic colonization impractical. Maybe we're truly alone, the first intelligence to arise in our cosmic neighborhood, bearing the awesome responsibility of being the universe's consciousness awakening to itself. These are philosophical questions more than scientific ones, at least for now. We lack data. We have one example of life, one example of intelligence, and from a single data point, you cannot determine a trend. But the questions are worth pondering, because they go to the heart of why we do astronomy, why we build telescopes, why we explore the cosmos. We want to know where we came from. We want to know where we fit in the grand scheme of things. We want to know if we're alone. And every discovery, every new piece of the cosmic puzzle, brings us incrementally closer to answers. Webb's observations of impossibly early galaxies remind us how much we still don't understand, how vast the unknown remains. But they also remind us how far we've come. A century ago, we didn't know galaxies existed beyond the Milky Way. We thought the universe was static. We had no idea about the Big Bang, dark matter, dark energy, black holes, neutron stars, exoplanets. Now we routinely observe galaxies billions of light-years away. We measure the universe's expansion rate and composition, we detect gravitational waves from colliding black holes, we find planets around other stars, we send robots to explore Mars and probes to the outer solar system and beyond. The pace of discovery is breathtaking. Each generation of astronomers sees things their predecessors couldn't have imagined. When Hubble launched in 1990, it revolutionized astronomy with its sharp images and deep observations. Now Webb is doing the same, pushing further, seeing deeper, revealing the universe with unprecedented clarity. And there will be telescopes after Webb, even more capable, continuing the tradition of exploration that defines our species. We are curious beings. We want to understand. We build tools to extend our senses, to see what our eyes alone cannot, to detect what our bodies alone cannot feel. And through these tools, we reach across space and time, connecting with the distant cosmos, reading the messages written in starlight. Every photon that enters Webb's mirrors began its journey in the distant past, carrying information about conditions in the early universe. These are not just abstract data points. They're messengers, emissaries from cosmic epochs we can never visit. They've traveled across expanding space for billions of years, surviving the journey, finally arriving at our telescope where we catch them, record them, analyze them, extract their secrets. It's an intimate connection with deep time, a conversation across the ages. The light from these impossibly early galaxies left its source when the universe was young, when our galaxy didn't exist, when the atoms in our bodies were scattered across intergalactic space. Not yet collected into stars and planets and living things. That light has crossed most of cosmic history to reach us now, in this moment, allowing us to witness events that transpired in the universe's childhood. There's something profoundly moving about this. We are the universe looking at itself, examining its own past, piecing together its own story. The atoms in our bodies were forged in the cores of long-dead stars, scattered through space by stellar explosions, collected by gravity into new stars and planets, assembled into molecules, into cells, into complex organisms capable of thought and wonder. We are star-stuff contemplating stars, as Carl Sagan famously said. And now we're using our consciousness, our technology, our accumulated knowledge to probe the deepest mysteries of existence, to ask how the universe began, how it evolved, where it's going, whether we're alone, what it all means. Perhaps there's no ultimate meaning, no cosmic purpose beyond what we create ourselves. Perhaps the universe is fundamentally purposeless, governed by physical laws that operate without intention or goal. But even if that's true, there's meaning in the act of seeking understanding, in the human endeavor to make sense of the cosmos. There's beauty in the equations that describe nature's workings, elegance in the way mathematics captures physical reality, wonder in the discoveries that each generation makes. We may be tiny, ephemeral beings on a small planet in an ordinary galaxy in a vast universe, but we're also minds capable of grasping cosmic truths, of understanding our place in space and time, of appreciating the grandeur of it all. Webb's observations of early galaxies are humbling. They remind us how much we don't know, how often the universe surprises us, how our theories, no matter how successful, are always approximations of reality rather than reality itself. But they're also inspiring. They show that discovery is ongoing, that there are always new horizons to reach for, new mysteries to solve, new wonders to uncover. The universe keeps revealing itself, layer by layer, each revelation raising new questions even as it answers old ones. What will we find next? What other surprises await us in Webb's data, in observations from future telescopes, in calculations from theoretical physicists, in simulations run on tomorrow's supercomputers? We cannot know. That's the joy and frustration of science. We're exploring uncharted territory, following evidence wherever it leads, constructing knowledge incrementally, sometimes facing dead ends or false starts, but gradually building a coherent picture of reality that becomes more accurate, more comprehensive, more predictive over time. The story of the universe is still being written. We're living through a chapter where our understanding is being tested and refined, where comfortable certainties are being questioned, where new vistas are opening up. Future generations will look back on this era and see it as a turning point, a time when the James Webb Space Telescope and other instruments revealed aspects of the cosmos that forced reconsideration of fundamental theories. They'll see our confusion, our debates, our false starts, but they'll also see our persistence, our creativity, our determination to understand truth regardless of how challenging it becomes. And perhaps they'll have their own surprises awaiting them, their own discoveries that challenge their theories, their own mysteries to grapple with. The universe is deep. Reality has layers within layers. No matter how much we learn, there's always more to discover. That's not a flaw or limitation. That's the gift of being conscious beings in a complex cosmos. There's always another question to ask, another observation to make, another calculation to run, another insight to pursue. So as we stand here now, confronted by images of galaxies that shouldn't exist, by structures that formed too early, by a universe that refuses to behave according to our expectations, what should we feel? Confusion, certainly. Humility, absolutely. But also excitement, anticipation, a sense that we're on the verge of something profound. These galaxies are not impossible. They exist. We can see them. What's impossible is our current understanding, which means our understanding is incomplete and awaits completion. That's where we are. That's the challenge before us. And that's what makes this moment in the history of astronomy so exhilarating, so pregnant with possibility, so fundamentally important. The universe is speaking to us through these ancient photons, through Webb's data, through the tension between observation and theory. It's telling us we have more to learn, deeper to dive, further to reach. It's inviting us to revise our story, to broaden our perspective, to embrace complexity and uncertainty as necessary companions on the path to understanding. And we will respond, as humans always have, with curiosity and ingenuity, with skepticism and openness, with rigor and imagination. We will solve this puzzle eventually, or at least get closer to solving it. And in doing so, we'll add another chapter to the grand story of cosmic discovery, a story that began with ancient peoples looking up at the night sky and wondering what those points of light were, and continues today with the most sophisticated telescope ever built revealing wonders our ancestors couldn't have dreamed of. The journey continues. The questions multiply. The universe awaits. And somewhere in the data, in the observations, in the minds of scientists working on this problem, the answer is emerging, slowly taking shape, promising to transform our understanding once again. This is science at its finest, humanity at its most ambitious, consciousness reaching toward truth across the vast distances of space and time. Whatever we discover, however the story resolves, the act of seeking, the dedication to understanding, the refusal to accept comfortable ignorance over challenging knowledge, these are what make us human, what make us worthy of the consciousness the universe has somehow, improbably, impossibly granted us. In the end, perhaps the most profound implication of Webb's discoveries is not about galaxies or the Big Bang or cosmological models. It's about us, about our capacity to be surprised, to question, to revise our understanding in light of evidence. It's about our place as meaning makers in a universe that may have no intrinsic meaning, as pattern finders in a cosmos governed by law and chance, as temporary arrangements of matter that have become aware, that can think and feel and wonder and understand. We are the universe's way of knowing itself, and through our telescopes and equations and theories, we're fulfilling that cosmic purpose, exploring the mystery of existence from the inside, participants and observers simultaneously, finite beings contemplating infinity, mortal minds grasping eternal truths. The galaxies that shouldn't exist remind us that reality is richer than our theories, that the universe has depths we've barely begun to plumb, that wonder and discovery remain possible no matter how much we think we know. They challenge us to think bigger, reach further, question deeper. They invite us to embrace the unknown not as an enemy to be conquered but as a frontier to be explored, an opportunity to expand our understanding, to grow our knowledge, to become more than we were. And in rising to that challenge, in building our telescopes and analyzing our data and debating our theories and pushing toward truth, we honor the cosmic legacy that made us possible, the 14 billion years of evolution from primordial simplicity to the complexity of minds capable of contemplating their own origins. This is the meaning we create, the purpose we forge from purposelessness, the significance we find in a universe that may be fundamentally indifferent to our existence but has nonetheless given rise to beings who care, who wonder, who seek understanding. Webb's impossible galaxies are a gift, an invitation to grow, a reminder that the universe still has secrets to reveal to those patient and dedicated enough to look. And we will look. We will seek. We will find. Because that is what we do. That is what we are. Explorers of the cosmos, students of nature, seekers of truth, children of the stars, forever reaching toward the light. The implications ripple outward from cosmology into every corner of fundamental physics. If the early universe operated under different conditions than we understood, what does this mean for our theories of quantum gravity, that elusive framework that would unite Einstein's relativity with quantum mechanics? The Big Bang represents the ultimate quantum gravitational event, a moment when all the matter and energy of the universe was compressed into a region so small, so dense, that both quantum effects and gravitational effects should have been equally important. Yet we have no confirmed theory of quantum gravity. String theory, loop quantum gravity, and other candidates remain speculative, untested directly. Webb's observations might be offering us indirect evidence, hints about how physics operates in regimes we cannot recreate in laboratories, clues written in the distribution of ancient galaxies. Consider the measurement problem in quantum mechanics, that fundamental puzzle about how quantum superpositions collapse into definite outcomes. Does consciousness play a role? Does observation itself create reality? Or is there some objective process, some mechanism we haven't identified, that determines which of many possible quantum states becomes actual? In the early universe, before observers existed, before consciousness emerged anywhere in the cosmos, quantum fluctuations were occurring at every scale. These fluctuations, amplified by cosmic inflation, became the density variations that eventually grew into galaxies. But what made those quantum fluctuations real rather than merely potential? What collapsed the wave function of the universe itself? These questions have haunted physicists since quantum mechanics was formulated nearly a century ago. Most physicists adopt an instrumentalist approach, treating quantum mechanics as a calculation tool without worrying too much about its metaphysical implications. But cosmology forces the issue. We're trying to explain the origin of everything, and quantum mechanics seems essential to that explanation, yet we don't fully understand what quantum mechanics is telling us about the nature of reality. The early galaxies Webb observes are descendants of quantum fluctuations, actualized possibilities that emerged from a sea of potential. Their existence testifies to some process, some mechanism that made the possible real. Understanding that mechanism might require revising not just cosmology but quantum theory itself. Then there's the holographic principle, that strange idea emerging from black hole physics suggesting that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. If the universe itself is holographic, if our three-dimensional reality is somehow a projection from information encoded on a distant cosmic horizon, this could have profound implications for how structure forms and evolves. Time itself might be emergent rather than fundamental, arising from more basic quantum entanglement relationships. Space might be an illusion, a useful approximation for describing phenomena that fundamentally exist in some other, more abstract realm. These ideas sound like science fiction, but they're being seriously explored by theoretical physicists grappling with the deepest questions about reality. And perhaps the early universe, that crucible where all the forces and fields and particles were unified under conditions of extreme energy and density, holds clues about these fundamental questions. Perhaps the rapid galaxy formation Webb observes is a signature of processes that only make sense when we view the universe holographically, or when we properly account for quantum entanglement at cosmic scales, or when we recognize that time and space are not the fundamental entities we've always assumed. The psychological impact of these discoveries on the scientific community deserves examination. Scientists are human beings with egos, careers, reputations invested in particular ideas. When observations threaten cherished theories, the response is not always purely rational. Thomas Kuhn, in his influential book on scientific revolutions, argued that paradigm shifts in science are as much sociological as logical, involving generational change as much as evidence accumulation. Older scientists, heavily invested in existing frameworks, often resist radical revisions. Younger scientists, with less to lose and more to gain from new paradigms, often drive revolutionary changes. We may be witnessing such a generational transition now. Established cosmologists, who built the Standard Model and spent decades refining it, naturally defend it against what they see as premature obituaries. They point out, correctly, that Webb's observations are preliminary, that systematic uncertainties remain unquantified, that alternative explanations haven't been exhaustively explored. Their caution is warranted, scientifically valuable, a bulwark against hype and overinterpretation. But younger researchers, unburdened by decades of commitment to specific models, are more willing to entertain radical possibilities, to propose exotic physics, to imagine that the universe might be fundamentally stranger than the Standard Model allows. Both perspectives are necessary. Science needs both conservatism and radicalism, both skepticism and openness, both rigorous defense of established knowledge and willingness to abandon it when evidence demands. The tension between these poles drives progress, preventing both ossification and chaos. What matters is that evidence ultimately decides, that observations rather than authority or tradition or personal preference determine which ideas survive and which perish. Yet we must acknowledge the limits of evidence itself. No observation is theory neutral. Every measurement requires interpretation through some conceptual framework. When Webb detects photons from a distant galaxy, converting them into an image, that image doesn't simply show us reality as it is. It shows us reality as filtered through our instrumentation, processed through our data reduction pipelines, interpreted through our theoretical assumptions about redshift, distance, galaxy evolution. At every stage, human choices and theoretical commitments shape what we see. This doesn't mean observations are arbitrary or that all interpretations are equally valid. It means that extracting truth from data is harder than it appears, requiring constant vigilance against bias, systematic error, and the seductive appeal of seeing what we expect to see. The replication crisis in other sciences should make us humble. Psychology, medicine, even experimental physics have discovered that many published results cannot be reproduced, that statistical flukes and publication bias and researcher degrees of freedom can create false positives, apparent discoveries that vanish under scrutiny. Astronomy has some protection against these problems because celestial objects are publicly observable, because independent teams can verify surprising claims. But systematic errors can still mislead entire communities. Distance measurements could have unrecognized biases. Stellar population models could have systematic flaws that affect all mass estimates similarly. Selection effects could make atypical objects seem typical. Acknowledging these possibilities is not defeatist. It's realistic. It keeps us honest. It reminds us that scientific conclusions are always provisional, always subject to revision, always dependent on assumptions that might turn out to be wrong. This epistemic humility is science's strength, not its weakness. It's what allows science to self-correct, to improve, to converge on truth despite the flaws and limitations of individual scientists and individual studies. Meanwhile, the public watches with mixed fascination and confusion. Headlines proclaim that the Big Bang has been disproven, that cosmology is in crisis, that scientists don't know what they're doing. These narratives are misleading, but they tap into genuine public skepticism about scientific authority. In an era of misinformation, of declining trust in institutions, of politicized science, communicating uncertainty without undermining confidence in science becomes increasingly difficult. How do you explain that the Big Bang model is both extremely well supported and potentially in need of significant revision? How do you convey that scientists' admission of uncertainty is a sign of integrity rather than incompetence? This communication challenge matters because public support sustains science. Webb cost $10 billion. Future telescopes will cost similar amounts. Fundamental research doesn't generate immediate economic returns. Its value is cultural, intellectual, existential. We fund it because we believe understanding our universe is worthwhile, because we value knowledge for its own sake, because we want to know our cosmic origins and destiny. But maintaining that support requires public engagement, requires helping people understand why these questions matter, why revising our theories in light of new evidence is exciting rather than embarrassing, why the scientific process, with all its messiness and uncertainty, is humanity's best tool for understanding reality. The philosophical traditions of different cultures offer varied perspectives on the questions cosmology raises. Western philosophy, with its emphasis on rationality and empiricism, has generally embraced the scientific project of understanding the universe through observation and reason. But other traditions approach cosmic questions differently. Buddhist cosmology speaks of infinite universes and cycles of creation and destruction spanning incomprehensible timescales. Hindu texts describe cosmic ages lasting billions of years, presciently close to modern estimates. Indigenous cosmologies often emphasize humanity's embeddedness in nature rather than separation from it, viewing the cosmos as alive, ensouled, interconnected in ways Western science has only recently begun to appreciate through concepts like ecology and systems theory. These alternative frameworks don't provide scientific theories in the modern sense, but they offer different ways of relating to cosmic mysteries, different vocabularies for expressing wonder and humility before the vastness of existence. Perhaps the crisis in cosmology is an opportunity for cross-cultural dialogue, for recognizing that science, powerful as it is, doesn't exhaust human wisdom about the universe. Scientific theories are models, useful fictions that capture aspects of reality while necessarily simplifying and abstracting. Other traditions remind us that reality exceeds our models, that the universe is not just an object to be understood but a context we inhabit, a mystery we participate in. The mathematics underlying modern physics is itself mysterious. Why should the universe be mathematical at all? Why should human-invented symbols and equations correspond so precisely to physical reality? Eugene Wigner called this, the unreasonable effectiveness of mathematics, recognizing that the deep connection between mathematical structures and physical phenomena is unexplained, perhaps inexplicable. We use mathematics as a tool, discovering that certain equations describe nature with uncanny accuracy, but we don't really know why this works. It's tempting to say mathematics is the language of the universe, but that just pushes the mystery back a step. Why that language? Why any language? What does it mean for physical reality to embody abstract mathematical relationships? Some physicists, like Max Tegmark, have proposed that the universe simply is mathematics, that physical reality and mathematical structure are identical, that what we call the physical universe is just one particular mathematical object in a vast landscape of possible mathematical structures. This mathematical universe hypothesis is deeply weird, erasing the boundary between abstract and concrete, suggesting that numbers and equations are not human inventions or discoveries but the fundamental fabric of existence itself. If true, it would mean that every consistent mathematical structure exists as a physical universe somewhere in an inconceivably vast multiverse of mathematical possibilities. Whether or not such radical ideas are correct, they illustrate how deeply puzzling existence is when you really think about it. Why is there something rather than nothing? Why this something rather than some other something? Why are the laws of physics what they are rather than different? These questions may have no answers, at least not answers accessible to human understanding. But asking them, grappling with them, exploring their implications, this is part of what gives human existence meaning and depth. The future of cosmology will likely involve technologies we can barely imagine today. Quantum computers might simulate cosmic evolution with unprecedented fidelity, modeling every galaxy, every star, every planet in vast regions of spacetime. Artificial intelligence might discover patterns in astronomical data that human scientists would never notice, formulating hypotheses and designing observations autonomously. Gravitational wave astronomy is just beginning, having detected its first signals only in 2015, but future detectors might observe gravitational waves from the Big Bang itself, testing our theories of the universe's earliest moments directly. Neutrino astronomy, still in its infancy, might reveal processes in stellar cores and galactic centers currently hidden behind veils of gas and dust. Space-based interferometers, arrays of telescopes flying in formation and combining their light, might achieve angular resolutions thousands of times better than any single telescope, imaging the surfaces of stars in distant galaxies, watching planets form around nearby stars, perhaps even detecting the atmospheric signatures of life on Earth-like worlds. Far future concepts involve telescopes that use the Sun itself as a gravitational lens, positioning spacecraft in the solar system's outer reaches where the Sun's gravity bends light from distant objects, creating magnifications that could image exoplanets directly, resolve details on their surfaces, detect cities if any exist. These are not fantasies. These are extrapolations of existing technology, ambitious but feasible projects that could be realized within this century given sufficient will and resources. What might such instruments discover? What revisions to cosmology might they necessitate? What new mysteries might they reveal? We cannot know, but we can be confident that whatever we discover will surprise us, will challenge our assumptions, will push our understanding in unexpected directions. And if we do find evidence of extraterrestrial intelligence, if we detect technosignatures or receive messages or make contact, how will that change our perspective on cosmic history? Intelligent life elsewhere would be the product of that same evolutionary history we're trying to understand, emerging from galaxies and stars and planets whose formation we're studying. Learning that consciousness arose multiple times independently would tell us something profound about the universe's capacity to generate complexity and awareness. Learning that we're alone, if we ever become confident of that through extensive searching, would be equally significant, imposing on us the awesome responsibility of being the universe's sole witnesses, perhaps its sole meaning makers. But perhaps the most important lesson from Webb's observations is one we should have learned already but keep forgetting: nature is under no obligation to conform to our expectations. The universe doesn't care what we think should be possible. It simply is what it is, and our theories must accommodate themselves to reality, not the other way around. Every time we've assumed we had nature figured out, every time we've thought our theories were complete, nature has surprised us with phenomena we didn't anticipate, forcing us to revise and expand our frameworks. This pattern has held throughout the history of science. Newtonian physics seemed complete until it couldn't explain Mercury's orbit or the behavior of light. The addition of relativity and quantum mechanics revolutionized physics but left us with two theories that can't be reconciled at the deepest level. The Standard Model of particle physics explains 3 of the 4 fundamental forces with remarkable precision but leaves out gravity and requires arbitrary seeming parameters that beg for explanation. Cosmology explained cosmic expansion and structure formation but had to invoke dark matter and dark energy, mysterious entities comprising 95% of the universe's contents, to match observations. At each stage, the solution to one set of problems raised new questions, revealed new mysteries, pushed the horizon of the unknown back rather than eliminating it. There's no reason to think this pattern will end. Understanding how galaxies formed in the early universe will reveal new puzzles about even earlier epochs. Discovering what dark matter is will raise questions about why it has the properties it does. Detecting dark energy's nature will prompt questions about its origin and evolution. Each answer generates new questions, each solved mystery illuminates unsolved ones, each expansion of knowledge reveals vaster territories of ignorance beyond. This might seem frustrating, but it's actually wonderful. It means the universe is inexhaustible, that curiosity can never be fully satisfied, that there will always be more to explore, more to discover, more to understand. It means that science is not approaching some final theory, some ultimate explanation that would render further investigation unnecessary. Instead, science is an infinite game, a perpetual journey into deeper understanding that has no final destination because reality has no bottom layer, no ultimate level of explanation where questions finally cease. Some physicists dream of a theory of everything, a single equation or framework that would unify all forces and explain all phenomena. String theory and its variants are presented as candidates for this ultimate theory. But even if we discovered such a theory, even if we had equations that accurately described all physical processes, we would still face the meta-question: why that theory and not another? Why do those equations describe our universe? A theory of everything would not be an explanation of everything, because explanation requires something outside the system being explained, some broader context or deeper principle. The ultimate theory would float free, unexplained and inexplicable, a brute fact about reality that we could discover but not justify. Moreover, even with a complete fundamental theory, we would not have complete understanding. Complex systems exhibit emergent properties that, while perfectly consistent with underlying laws, are not predictable from those laws alone. You cannot deduce the existence of hurricanes from the Navier-Stokes equations or the behavior of ant colonies from the biochemistry of individual ants or the emergence of consciousness from neuroscience and quantum mechanics. These higher-level phenomena require their own vocabularies, their own explanatory frameworks. A theory of everything would not make chemistry, biology, psychology, sociology, or any other special science obsolete. It would not explain meaning, purpose, beauty, or any of the things humans care most about. So even if cosmology eventually resolves the current puzzles, even if we understand how galaxies formed and why the early universe looks the way Webb shows us, we will not have explained everything that matters about existence. We will have answered one class of questions while others remain, while still others emerge. This is not a limitation to lament but a feature to celebrate. It means the universe is richer than any theory, that reality overflows our attempts to capture it in equations and models, that there will always be room for wonder, always space for mystery, always new frontiers beckoning. The human element in all of this cannot be forgotten. Every telescope, every observation, every theory, every debate represents countless hours of human effort, human creativity, human dedication to understanding. Graduate students work late nights analyzing data, writing code, running simulations. Postdocs hustle for positions in a competitive job market, trying to establish their research programs while facing uncertain career prospects. Professors juggle teaching, research, administration, grant writing, mentoring, serving on committees. Engineers design and build instruments, solving technical problems that have never been solved before. All of these people are motivated by something beyond money or fame, something deeper, curiosity, the desire to understand, the satisfaction of contributing to human knowledge. Many will never be famous. Most will not make revolutionary discoveries. The vast majority of scientific papers are read by a handful of specialists and forgotten. But every contribution matters. Science is cumulative, collective, a species-wide endeavor where small incremental advances by many individuals gradually build toward major breakthroughs. The scientist who carefully calibrates an instrument, who notices a subtle systematic error, who develops a slightly better analysis technique, who mentors a student who goes on to do great work, all of these contribute to the enterprise even if their names never appear in textbooks. This is important to remember in an age that worships individual genius and revolutionary breakthroughs. Science is not primarily about lone geniuses having eureka moments. It's about communities of researchers collaboratively building knowledge, testing each other's work, correcting errors, refining ideas, gradually converging on truth through collective effort. Yes, individual brilliance matters. Yes, some scientists contribute more than others. But even Einstein built on the work of Maxwell, Lorentz, Poincaré, and others. Even Newton acknowledged standing on the shoulders of giants. Great scientists are nodes in networks, not isolated peaks rising from nothing. And the network extends beyond professional scientists to include science educators, communicators, enthusiasts, citizens who support research through taxes and donations, everyone who values knowledge and understanding. Science is a human endeavor in the fullest sense, depending on social institutions, cultural values, economic support, political will. Keeping that web of support strong requires demonstrating that science matters, that it enriches human life, that it addresses questions people care about even if not always in ways that generate immediate practical applications. Webb's discoveries serve this purpose beautifully. They capture public imagination precisely because they touch on ultimate questions, because they hint at revisions to our deepest understanding of reality, because they demonstrate that the universe still has surprises in store, that human knowledge remains incomplete, that the adventure of discovery continues. When people see Webb's images, when they read about impossibly early galaxies, when they hear scientists debating what it all means, they're reminded that the universe is mysterious and magnificent, that human ingenuity can reach across billions of light years and billions of years, that we are capable of grasping cosmic truths despite our smallness and brevity. This sense of connection to something larger than ourselves, this participation in the grand project of understanding existence, this is what science offers beyond its practical applications. It provides meaning, purpose, transcendence, all the things religion traditionally offered but grounded in evidence and reason rather than faith and revelation. For many people, science has become a source of spiritual sustenance, a way of relating to the universe that satisfies both intellectual and emotional needs. The awe inspired by cosmological discoveries is not fundamentally different from religious awe, that feeling of confronting something vast and incomprehensible that puts our concerns in perspective while simultaneously making us feel connected to the whole. Whether we frame it religiously or scientifically or philosophically, the basic existential situation remains: we find ourselves existing, we don't know why, we're trying to make sense of it all. Science is one approach to that challenge, remarkably successful by certain measures, limited by others. It can tell us how the universe evolved, how galaxies formed, how stars create heavy elements, how planets coalesce from protoplanetary disks, how life emerged from chemistry, how consciousness arose from evolutionary pressures. What it struggles with are the why questions that lie beneath the how questions. Why does the universe exist at all? Why are we here? What are we supposed to do with our existence? What happens when we die? These questions may be unanswerable, at least by science. They may even be malformed. Assuming purposiveness where none exists, projecting human concerns onto an indifferent cosmos. But they're the questions humans actually ask, the questions that drive much of our behavior, the questions that give shape to our lives. A complete account of human relationship to the universe must acknowledge both what science can tell us and what it cannot, both the power of the scientific method and its limitations. As we stand at this moment in cosmic history, confronting observations that challenge our theories, we're participating in something ancient and ongoing, the human attempt to understand our place in existence. That attempt takes many forms across cultures and throughout history. Shamans seeking visions, philosophers constructing logical arguments, mathematicians exploring abstract structures, astronomers building ever more powerful telescopes, all are engaged in the same fundamental project, making sense of this strange fact that we exist in a universe we didn't create and don't fully comprehend. Webb's impossible galaxies are a gift to this project. They're data points, yes, but they're also provocations, invitations to think differently, reminders that reality exceeds our grasp. They keep us humble. They keep us curious. They keep us engaged with the cosmos rather than retreating into narrow human concerns. They remind us that we're participants in a story much larger and longer than our individual lives, than our civilizations, than our species. We're inheritors of 14 billion years of cosmic evolution, beneficiaries of countless chance events and necessary conditions that had to align for us to exist at all. That inheritance brings responsibility. We're the universe's consciousness, at least in our local patch of spacetime, at least for now. What we do with that consciousness matters. Do we use it to understand, to appreciate, to preserve and enhance the complexity and beauty that evolution has generated? Or do we squander it on trivialities, destroy the biosphere that sustains us, fail to pass on knowledge to future generations? These choices are ours to make, and they have cosmic significance precisely because consciousness is so rare, so fragile, so precious in a universe that is mostly void and silence. Looking out at those ancient galaxies, seeing structures that existed billions of years before Earth formed, we're reminded of our cosmic context. We're not the center of the universe. We're not its purpose. We're not even particularly special in any objective sense, just one more arrangement of matter that happens to be self-aware. But perhaps that awareness itself is special enough. Perhaps consciousness, wherever and however it arises, is the universe's way of giving meaning to what would otherwise be a meaningless process of matter and energy evolving according to blind physical law. If that's true, then our scientific investigations are not just satisfying curiosity or advancing knowledge. They're fulfilling a cosmic function, actualizing a potential inherent in the universe from its beginning. The atoms in our telescopes, in our computers, in our brains, were forged in stellar cores, scattered through space, assembled by gravity and chemistry into the complex systems that can now comprehend their own origins. That's not just a fact. That's a miracle, not supernatural but natural, not violating physical law but embodying it, not imposed from outside but emerging from within. The journey from the Big Bang to Webb, from primordial plasma to sophisticated instruments detecting ancient light, from unconscious matter to conscious minds pondering their place in existence, this journey is what we're trying to understand. And perhaps the most profound realization is that the journey has no end. There is no final understanding, no ultimate explanation, no point where the questions stop. There is only the ongoing process of inquiry, discovery, revision, deeper inquiry, deeper discovery. Those ancient galaxies shine in Webb's images like beacons from the past, carriers of information about cosmic dawn, about the universe's youth, about conditions we can study but never visit. They've traveled through space and time to reach us. And in receiving their light, in analyzing their spectra, in puzzling over their impossible properties, we're completing a circuit billions of years in the making. We're the present confronting the past, the evolved contemplating the primordial, consciousness examining its own ancestry. And what we find there challenges us, surprises us, forces us to reconsider. That's as it should be. That's how growth happens, how understanding deepens, how wisdom accumulates. If the universe simply confirmed our expectations, if observations always matched theories, if there were never any surprises, science would be boring, pointless, complete. The fact that nature keeps surprising us, that reality refuses to fit neatly into our frameworks, that mysteries remain despite centuries of investigation, this is not frustrating. This is thrilling. This is the universe inviting us to keep exploring, keep questioning, keep reaching toward deeper truth. So we accept the invitation. We build better telescopes. We develop new theories. We make predictions and test them. We argue and collaborate and compete and cooperate. We teach the next generation. We share what we learn. We persist in the face of uncertainty, confusion, contradiction. We trust that the process works even when individual results prove wrong. We maintain faith not in any particular theory but in the method itself, the scientific approach of observation, hypothesis, testing, revision. This is our heritage and our responsibility, passed down from ancestors who first wondered about the stars and will be passed to descendants who will wonder about things we cannot imagine. We're links in a chain of understanding that stretches from the distant past into the distant future, each generation adding its knowledge, correcting previous errors, making possible further advances. The chain may break if we don't maintain it, if we allow ignorance or dogmatism or short-term thinking to triumph over curiosity and reason and long-term perspective. But if we keep it intact, if we preserve and extend the scientific tradition, future generations will look back at our time and see it as we see the time of Copernicus or Newton or Einstein, a period of transition, when old certainties gave way to new understanding, when observations forced theoretical revision, when human knowledge took another step toward comprehending the cosmos. The galaxies that shouldn't exist according to our theories do exist according to reality, and that mismatch is where knowledge grows. Between what we think we know and what actually is lies the frontier, the space where science happens, where minds engage with mystery and occasionally wrest from it fragments of understanding. This is sacred work in its own way, not because it's ordained by any deity but because it honors the capacity for understanding that somehow emerged from the universe's evolution. We don't know why we can understand anything at all, why the universe is comprehensible rather than chaotic, why consciousness arose that can grasp physical law and mathematical structure. But it did, we do, and making the most of that improbable gift means continuing the work of inquiry, continuing the search for truth, continuing the conversation across generations about what exists and why. In this moment, as Webb's data flows in, as theories are tested and refined, as scientists debate and calculate and observe, we're watching human knowledge evolve in real time. It's messy and uncertain and contentious because that's what progress looks like from the inside. Only in retrospect does it appear smooth and inevitable. Living through it means accepting ambiguity, tolerating contradiction, remaining open to revision while maintaining confidence that the process ultimately leads toward better understanding. The universe we inhabit is stranger and more wonderful than we imagined, and those early galaxies shining in Webb's images are proof of that strangeness and wonder. They defy our expectations not to frustrate us but to teach us that expectations based on limited knowledge are always provisional, always subject to update. They invite us to expand our minds, to think bigger, to imagine possibilities we've overlooked. They challenge the comfortable certainty that we've got things basically figured out and only details remain. They remind us that reality is richer than any theory, that the cosmos has depths we've barely begun to explore, that the adventure is far from over. And so we continue. We look deeper into space and further back in time. We build instruments of greater sensitivity and power. We develop theories of increasing sophistication. We train our minds to think about time scales spanning billions of years, distance scales spanning billions of light years, processes operating at energies and densities impossible to recreate on Earth. We push the boundaries of human understanding outward, knowing we'll never reach a final boundary, knowing the horizon will always recede as we approach it, knowing that every answer reveals new questions we couldn't have formulated before. This is the human condition in a universe that appears to be infinite in both its vastness and its complexity. We are finite beings with finite minds confronting infinity, and the remarkable thing is not that we fail to grasp it completely but that we can grasp it at all, that we can comprehend cosmic scales and processes despite our smallness and brevity, that we can construct theories encompassing the entire history of the universe despite being confined to one tiny planet for one brief moment in cosmic time. The galaxies Webb has revealed to us exist whether we understand them or not. They shine their light across the void, indifferent to our theories, unconcerned with our debates. But we are not indifferent. We care desperately about understanding them because understanding the universe is, in some deep sense, understanding ourselves. We are made of the same matter, governed by the same laws, products of the same evolutionary history. When we study galaxies, we study our ancestry. When we probe the Big Bang, we investigate our origins. When we ask how structure arose from chaos, we ask how we arose from the cosmos. These questions have no final answers, only better and worse approximations, deeper and shallower understandings. The James Webb Space Telescope has given us new data that demands better approximations, deeper understanding. It has shown us a universe that formed faster, organized sooner, achieved complexity more quickly than our theories predicted. Whether this requires minor adjustments or major revisions remains to be seen, but either way, we emerge with knowledge closer to truth than before. And truth, however imperfectly we grasp it, however provisionally we hold it, however certainly it will be refined by future generations, truth is what we seek. Not because it makes us comfortable, not because it confirms our prejudices, not because it tells us what we want to hear, but because truth is the map that corresponds to the territory, the theory that matches reality, the understanding that allows us to navigate existence with our eyes open rather than closed. The universe offers us truth in the form of photons arriving from distant galaxies, carrying information encoded in their wavelengths and intensities. We decode that information with our instruments and our mathematics and our theories. Sometimes the message surprises us. Always it teaches us. And in learning what the universe has to tell us, we become more than we were, we grow into the cosmic beings we have the potential to be, conscious participants in the grand unfolding of existence, witnesses to the universe's story, tellers of that story to each other and to generations yet unborn. This is who we are. This is what we do. This is why we build telescopes that cost billions and take decades to construct. This is why we spend our lives studying phenomena no human will ever experience directly. This is why we care about galaxies so distant their light has been traveling toward us since before our world existed. Because in knowing them, we know ourselves. In understanding the cosmos, we understand our place in it. In grasping how we came to be, we discover what we might become. The story continues. The mystery deepens even as understanding grows. The universe reveals itself slowly, reluctantly, one observation at a time, one theory at a time, one breakthrough at a time. We are patient because we must be, persistent because we choose to be, hopeful because the alternative is despair. And in our patience and persistence and hope, we honor the improbable gift of consciousness, the unlikely emergence of beings who can ask why and how and when and where, who can build instruments to extend their senses across space and time, who can construct theories explaining phenomena they cannot directly perceive. We are the universe knowing itself, however imperfectly, however partially. The galaxies in Webb's images, impossible according to our theories but undeniable in their existence, are the universe teaching itself, showing us where our understanding falls short, inviting us to try again, to think harder, to look deeper. And we accept that invitation because it is our nature to do so, because curiosity is as fundamental to us as gravity is to matter, because understanding is what gives human existence its deepest meaning and highest purpose in a cosmos that grants us neither except what we create for ourselves. The journey from ignorance toward knowledge has no destination, only direction. The path from confusion toward clarity has no end, only progress. We walk that path together, generation after generation, building on what came before, contributing what we can, passing forward what we've learned. And somewhere in that ongoing process, in that collective striving toward truth, we find meaning sufficient to justify existence, purpose adequate to orient our lives, transcendence enough to satisfy our souls even in a universe that may ultimately be indifferent to our presence but has nonetheless made possible our understanding, our appreciation, our wonder. This is enough. This has to be enough. Because this is what we have, each other, this moment, this universe revealing itself through our investigations, these mysteries inviting us forward into unknown territory where dragons no longer lurk but wonders surely await. The galaxies that shouldn't exist do exist, and their existence changes us, expands us, makes us larger than we were before we knew about them. Every discovery does this if we let it, if we remain open to transformation, if we allow reality to reshape our understanding rather than forcing reality into predetermined categories. And so we stand here, human beings on a small planet, building telescopes and theories, observing distant galaxies and pondering their implications, participating in the universe's self-exploration, temporary forms through which the cosmos examines itself. We will pass, as all forms pass, but what we learn may persist, carried forward by those who come after, added to the growing body of human knowledge about existence and its origins. This is our contribution, our legacy, our gift to the future, not final answers but better questions, not complete understanding but deeper comprehension, not the end of mystery but its ongoing exploration. The universe is vast beyond imagining and ancient beyond comprehending, yet here we are, part of it, products of it, conscious reflections of its improbable journey from simple beginning to complex present. The impossible galaxies shining in James Webb's images remind us that the journey is far from over, that the universe still holds surprises, that reality exceeds our theories as it always has and always will. And in that space between theory and reality, in that tension between expectation and observation, in that friction between what we think we know and what actually is, human understanding grows, and consciousness fulfills its cosmic function of bringing light to what would otherwise remain forever dark, making known what would otherwise stay forever unknown, giving voice to the universe's silent story that has been waiting 14 billion years for someone, somewhere, somehow, to finally be told.